Latitude Media, podcast at the frontier of climate technology.
I'm Shale Khan, and this is Catalyst.
We know how to make CO2 into graphene. Graphene is a superstructured, super light, super durable, super electrically conductive material. It's like a version of buckyballs, basically. We know we can do that. We can do it right now at like gram aliquots in laboratories. It's like hard to spin that into a fiber that can be used by a fighter pilot. We're not in that world yet. But there's good reasons to want to do that.
Decarbonization is going to require the transformation of 5.5 sectors of the economy. The 5 are energy, transportation, buildings, food and agriculture, and heavy industry. The half is carbon management. What should that half look like?
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shale Khan. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. So let's assume here as a starting point that we're going to capture a lot of CO2 in the coming decades, like billions of tons of CO2 per year. Some of that will come from point sources, ethanol refineries, bioenergy plants, maybe cement plants, maybe some power plants, et cetera. And then some is going to come directly from the atmosphere or from the oceans. It doesn't really matter for our purposes today. The question is, what are we and what should we do with all that CO2? Should we sequester it underground for thousands of years? Should we turn it into rock? Should we turn it into products? Should we turn it into fuels? What kinds of fuels, et cetera? The options and the trade-offs abound, which is basically a sentence that perfectly describes the type of thing I like to talk about on this pod. Hence, this conversation with Julio Friedman, who you've heard before. Julio is the self-proclaimed and now widely recognized carbon wrangler and actually has an official title as the chief scientist at Carbon Direct as well. Here's Julio. Julio, welcome back.
Always a pleasure. Thank you, Shale.
Let's talk about CO2 and what we're going to do with it. Before we talk about what we're going to do with it, right? The premise here is that in any successful world of combating climate change over the coming decades, we're going to start capturing, one way or another, we're going to start capturing gigatons, billions of tons of CO2, and we're going to have to decide what to do with all of that CO2. But I want to start with what we do today, because there, even prior to the world of, carbon removal, and even really before much point source capture existed, there is an existing market value chain infrastructure for CO2, the gas. So talk to me about where do we capture CO2 today? What do we do with it?
Sure. So there was 2 big markets that already existed for CO2 independent of climate. One of those was for enhanced oil recovery, and almost always that was taking CO2 out of the ground and then using it as a solvent to get more oil out of fields. The 5,000 miles of CO2 pipelines in the United States are largely dedicated to that. There's also a very large market for CO2, which is the food and beverage market. We use CO2 in meat processing. We use CO2 for dry ice. We put CO2 into beer and fizzy water. So those markets were also well established. It's important to know on the scale of climate, both those markets are very small. And so part of the challenge is we need to push forward in this new direction. The other thing about it, of course, is now we are doing it for climate. So we have something on the order of 47 facilities around the world that operating today that capture CO2 and keep it out of the air and oceans for climate. Broadly, that's about 60 million tons a year. That is not gigatons, but it's a whole lot more than a science experiment. That some people refer to this as like an unproven or untested technology. We got 5,000 miles of pipelines, we got hundreds of CO2 storage sites, and we're capturing and storing 60 million tons of CO2 a year.
And those are, of those 47, like what, 45 are point source, basically?
Yes. Most of the CO2 capture that is done is where CO2 is concentrated. There is an economic cost to separating and concentrating CO2. So you tend to start where you already have a separated and concentrated source of CO2. Ethanol plants, hydrogen facilities, natural gas processing facilities are the places that most of this is done today. Increasingly, though, again for climate, we are starting to capture from dilute sources. Those dilute sources are also representative of point sources. So a coal-fired power plant or a natural gas plant or a steel mill or some other kind of place. There are a couple of places, though, where we are pulling CO2 out of the air and oceans. And we are doing that because we know we have to, and because people will pay for it. And there are a couple of those around the world now, and there's many more coming online quickly.
Yeah. Okay. And so in the current state of the CO2 market prior to climate, I guess I should say, I think of it as being as you said, those two categories of end use. The infrastructure associated with those also kind of different, right? You said there's pipeline. We have 4,000 or 5,000 miles of pipeline in the United States to pipe CO2 around for enhanced oil recovery. And then on the food and beverage side, we truck CO2 around to those companies, and the big industrial gas companies like Air Liquide and Linde and so on. They deliver industrial gases, and CO2 is one of the gases they deliver, and they truck it to whoever needs it, basically.
Correct. And there's no contention around that. We have tube trucks that move volumes of CO2 from A to B. And the volume of that's not huge, but it's also not tiny. So it is pricier than a pipeline. So it costs something like $18 a ton or something like that to ship things by truck, where it might cost $2 a ton to ship it by pipeline. Right? So really, that's the transaction space. And if you're going to move very, very large volumes, you don't want thousands of trucks moving CO2 like every hour from point A to point B. It's just more sensible to move it by pipeline. Interesting thing I want to leave with your listeners, we are starting to see the repurposing of existing pipelines. We're starting to see people take existing natural gas pipelines and reverse them. And if they have the right metallurgy, and if they're suited for the pressures and temperatures involved, that's a great solution, because it means you don't have to build new infrastructure, and you also don't need to permit the new infrastructure. You can just move with existing rights of way and existing pieces of pipe.
Okay, so we have this, relatively speaking, small but meaningful existing value chain of, taking CO2 from point sources, shipping it around, and doing something with it. So let's fast forward ourselves, though, 10 years, 20 years, whatever it might be. And again, if we're going to be successful in combating climate change, that means we're going to be doing orders of magnitude more of this. We're going to be in the gigatons for sure, maybe in the tens of gigatons depending on what happens otherwise. So I want to talk about, in that world, what the options are for what we're going to do with the CO2. And in that world, we will, I think presumably continue to capture CO2 from a variety of point sources, and we will also be scaling up various forms of direct air capture. But for our purposes today, to some extent, it kind of doesn't matter. You end up with CO2 either way. You got to do something with that CO2. So talk me through high level. What do you think about being the sort of branching options for, you've got a bunch of CO2 gas that has been captured for climate purposes, I should say. What can you do with it?
Right. So the largest thing that we are going to do with the CO2, the biggest enterprise, is still going to basically be storage. It will be CO2 disposal in dedicated geological formations. If you look at the climate arithmetic that the International Energy Agency and the IPCC and other groups have put together, that is the fate and transport of a lot of the CO2. It just goes back into the Earth because we took it out of the Earth in the first place. It is geospheric return. And that is the sort of straightforward way of doing that. It's also relatively cheap. To turn CO2 into stuff usually takes energy or money. And so in the same way we only recycle a fraction of our produced goods of any kind, whether it's glass or aluminum or paper or whatever, we also will only recycle a fraction of the CO2. And I want to come back to the utilization part because the utilization part is fun and there's all kinds of awesome stuff happening in there. But if you just run the numbers, out of the, say, 6 gigatons that the IPCC believes we're going to need to do, 5.5 gigatons of that are going to be storage.
Right.
It's something like 90%.
That's a key point. Let's talk for a minute before we talk about utilization then about the permanent sequestration and storage world. I think listeners may be familiar with the emergence of these injection wells, Class 6 wells, as they're called in the United States, that are starting to pop up. Where are we in the trajectory of getting this stuff permitted, of actually doing injections? Everybody will tell you there is more than enough geology to support that much sequestration. But of course, to get there is going to require a big mobilization, a lot of regulatory support, and so on.
Yes. So again, I remind your listeners, this is not digging trenches and dumping CO2 in a hole. Like, that is not what we're doing. We are injecting CO2 miles underground, typically more than a mile. 1.5 to 2 kilometers is the typical injection point. And when you do that, you're not injecting a gas. You're actually injecting something that's a lot more like a liquid. It has the density of oil. It has the viscosity of oil. And so places where oil and gas is produced are good places to do it. And we have something like 10 to 20 trillion tons of storage capacity in those kinds of rocks. In order to do that, though, you have to permit these wells. And the regulations are pretty serious. These are well-regulated undertakings in developed countries, in the OECD, in North America, and Europe. And there's an extensive permitting process and rubric you go through. I'm pleased to say the United States has done a couple of things right. Number one, they've hired a bunch of regulators. We now have people to process these things. 3 years ago,
that's been an issue, right?
It has been an issue. But actually, in the bipartisan infrastructure law, there was money given to the EPA to hire and train regulators. So we're starting to move past that bottleneck, which is great. Another thing that has happened is in a number of cases, states have asked if they can execute that through their primacy option. This is important. Again, many people are confused about this. This is not a dilution or a diminution of the regulation. You have to put exactly as much stringency into that process as you do through the EPA itself. But we now have a handful of states, Louisiana, Wyoming, North Dakota, that have taken on primacy, and that means we have more people who can do this. And those people are more familiar with the operators involved, with the land involved, all these things. So there's some upsides and benefits from that. People have questions about, will it really be done that strictly? I think will remain to be seen. But in many cases in the past, for Class 1 wells, for Class 2 wells, for Class 5 wells, these kinds of primacy rules have enabled faster and better permitting. And we're starting to see the same thing happen in other countries too. In Europe, in the UK, this same kind of regulatory process is going well and is being executed faithfully.
Okay, so sounds like you're fairly bullish that we are going to be scaling up sequestration, underground sequestration capacity in a lot of countries. I guess one question, given what you said, right? IPCC expects 7 gigatons in total, and 6.5 of that is going to be sequestered underground. Why not 7? Like, why are we diverting any of it? Why is it not all effectively landfilled, quote unquote, underground?
The short reason why is because there's a couple of smart things you can do with CO2 that help in other dimensions. You can turn CO2 into pretty much anything. If your listeners look around the room, anything that is not glass or metal is made out of carbon. Doesn't have to be made out of carbon from oil or gas or coal. It could be made from carbon of any kind, from plants, from the air. And over the past 20 years, a lot of effort has gone into technology development and company development and infrastructure development that suits that use pathway. CO2 use, CO2 recycling, CO2 utilization, call it what you want. But there's a handful of stuff that's not crazy that you can turn CO2 into that makes economic sense, that makes environmental sense. And on that basis, we are starting this process of turning CO2 into the built world.
We'll talk about the specific things that are not crazy and what's happening in those in just a moment. But how do you define what is and what is not crazy? in this context?
Right. So in this regard, I am very much a student of Dr. Jennifer Wilcox, who is the Principal Deputy Assistant Secretary at the Department of Energy. Dr. Wilcox years ago said, hey, second law of thermodynamics, that's non-negotiable. Everything else is negotiable. So the first cut at this is, does it make sense according to the second law of thermodynamics? Are you just going to waste a bunch of energy and money turning it into stuff? And as a consequence, the very first hit in utilization space is, can we turn CO2 into stuff that requires no additional energy? And the answer is yes. Mostly you can turn it into concrete, you can turn it into aggregate, you can turn it into sand, you can turn it into stuff that we use huge volumes of. Every year the world uses 30 billion tons of concrete. So turning CO2 into concrete is a gigaton market, and it's not nuts. It actually releases energy. And in that context, you can scale that in a complex way, but it's straightforward. There's no magic involved. And now there's hundreds of companies that turn CO2 into those kinds of products. The other thing that you can turn CO2 into is fuel or chemicals. In order to do that, you need to add a lot of energy. Unsurprisingly, a lot of people figured out immediately, it better be clean energy or we're wasting everybody's time. So it better be energy that has very low carbon emissions, full and embodied, which immediately prompts the question, well then, shouldn't we be using that clean energy for other reasons? And that's the point where it starts getting into questions of geography, infrastructure, markets, policy. These other sort of questions start to matter, but you can still find a whole bunch of things that make sense.
How do you think about, I know you're a first principles thinker, and I've gone back and forth on this question myself. So fuels, right? The one that probably has garnered the most attention of late is e-fuels for aviation, so e-jet. And so that means you capture your CO2, you combine it with hydrogen, you got to produce that hydrogen somehow. You make yourself your drop-in jet fuel, with obviously some steps in between. As you said, doing that requires a fair bit of energy input into both the production of the hydrogen as well as the conversion of the CO2 and the hydrogen to syngas or whatever, and the process downstream to make jet fuel. The alternative from a societal perspective to doing that, of course, is just to continue using our fossil jet fuel today, and then do direct air capture and sequester it underground, right? And those two things happen in two separate places, but you net them out. And probably that ends up being, at least energetically, that's easier, right? So how do you think about the value of synthetic e-jet relative to the DAC sequestration alternative?
So the punchline here is we're going to do some of that, and we're going to do some of that for valid reasons. Let me unpack that for you, though, in three specific dimensions. One of them is, I do not know any policymaker or any CEO who wakes up in the morning and thinks, what's the thermodynamic and economic optimum?
Yeah, this is right. This is where I've sort of landed on it. It's like a practical reason.
Right. And so in that context, people grouse about the fact that we make water out of the tap from like 50 cents a cubic meter, 50 cents a ton for water. If you use a desal plant, it's more like $1 as opposed to 50 cents, but bottled water is like $7,000 a ton. Like there's all kinds of stuff where we just pay for a bunch of good reasons. And e-fuels and e-jet in particular are one of those places that makes a lot of sense. It's not necessarily that it is automatically cheaper or better, but we have regulatory environments like the Refuel EU that requires e-fuels. 0.7% of the fuels in Europe in 2030 are going to be e-fuels for jets by law. And that's in part to stimulate technology development, to see if this makes a viable climate options. There's reasons to do that. Another reason to do it is that the people who operate planes are disinterested in a deadweight economic cost. They could just pay $300 a ton or whatever to pull CO2 out of the air and oceans, but they're also saying we would rather have supply chain control. We would rather buy fuels that we understand the carbon content, where we might be able to source, where we might be able to invest and make money. And so companies like Boeing or Airbus, companies like United Airlines or Delta are looking at this and saying, we want to really understand the cost, the supply chains, the logistics, the value proposition for operators. We want to understand all this stuff for real in order to make smart decisions.
Yeah. It's one of these things where, like, if you were God and you could just make the decision on behalf of the world, probably just, purely energetically and economically, you'd probably just capture and sequester it. I suppose if you were God, you would never have created this problem in the first place, but set that aside. With that said, there is the reality of the world, and I've come to a similar conclusion myself, which is what's more likely to happen, actually, at scale, is the physical purchase of E-Jet, as opposed to, airlines just like carrying this massive deadweight cost on their books every single year for the next decades. That all it is them, paying for the avoidance of using E-Jet.
Right. And this is not at all a hypothetical decision. We are staring down the barrel of some very strong compliance requirements in aviation. Specifically, the International Civil Aviation Organization, ICAO, has put forward a set of standards over the past 15 years called CORSIA. And the CORSIA standards started as a voluntary program, but they become mandatory, wait for it, in 2027. That is 3 years from now. And they require companies to hit a certain threshold of purchasing low-carbon fuels and minimizing their fleet's footprint. And it's the UN, so it is all countries equally around the world. It's not like Germany does it and China doesn't. Like, all nations have to do this. If every sustainable aviation fuel plant that had been announced were to be built, there would not be enough fuel for the 2027 target. Period. So there's going to be some CO2 removal that is also a compliance option. But it starts with fuels and then goes to other things. And that has to happen really fast. Really fast. Too fast to build and permit the new plants. So on top of that, we are seeing companies scrambling hard to do everything they can to make these volumes. And some of it's the more conventional sustainable aviation fuels, like made from animal fats or made from soybeans. There are e-fuel companies. HIF Global is a company that makes synthetic fuels, and they turn CO2 into jet fuel the way you just described. Another one is a company called 12. Full disclosure, that is a portfolio company of one of our sister companies, Carbon Direct Capital. But they are building a synthetic jet fuel plant in the state of Washington. And in both cases, they're taking cheap CO2, they're taking atmospheric CO2, they're taking cheap electricity to turn it into hydrogen, they're doing the electrical chemical reduction of CO2 to carbon monoxide or some other state, and they're making jet. Like, these things are under construction. Like, this is not a science experiment either. Like, people are building and shipping stuff, and they've already got contracted offtake. So we'll know a lot more about this in 2 or 3 years, at which point we can decide, well, out of the 7 gigatons that we need to manage, how much of that's really going to go into jet?
Because it could be a lot. I mean, you said half a gigaton of the 7, but like, if it were true that E-Jet really took off, and in 2050, all of our jet fuel is E-Jet, it'd be way more than that.
Yes. What is also clear is we're not using less jet. There was this period of time where people thought we could just change human behavior and reduce total miles flied. Like, that is not happening. The miles flown are growing everywhere in the world. That trend will continue. And people have been trying to make planes that run on electricity, planes that run on hydrogen. It's really hard. Those timelines are also really far away. So we need to drop in fuel right away. And there is going to be some HEFA. There is going to be some alcohol to jet, like the LanzaJet guys are doing in Georgia. But there's going to be some e-fuels too. And as renewables get cheaper and cheaper, as carbon capture gets cheaper and cheaper, this becomes less problematic. Today, it's like 10 times the price of jet, but it won't be that forever. It might be 5 times, 3 times, 2 times. At what point is it okay to just pay that green premium?
I do want to make one side note, which I don't want to divert too long onto, but I want to say that the assumption as renewables get cheaper, I agree with that assumption in the long arc of history. But the delivered cost of electricity, the trajectory of it is the opposite direction. And I think is going to be the opposite direction for a while. So,
Oh,
like,
yes. It's almost like there's an electricity gauntlet.
it's almost like there's an electricity gauntlet, almost as if.
Right. So, and the thing is, the EU has actually baked this into their calculus. So they have a lot of CO2 capture in 2030, 30 million tons. That is a 6 times growth in 6 years. Okay, that's going to be really hard to pull off. But then they have 280 million tons in 2040, which is a 10 times growth in 10 years on top of that. And then it goes up to 450 million tons in 2050. That's the most recent EU plan and communique. That, by the way, reflects the more ambitious targets. This is not a greenwashing exercise. They're like, holy cow, as we get more and more ambitious, we're going to need to do more and more of this. That's part of their industrial carbon management strategy. In that same window, they start with point source capture. They start moving to biomass and direct air capture, and that fraction grows to 60%. At the same time, this is the utilization fraction. The utilization fraction today is 0. In 2050, the utilization fraction is like 40%. And most of that is for fuels. That is premised on the idea that in 2050, it will be cheaper. It's also premised on the reality that today it's not. And that today, if you had cheap electricity, you should use it to do other things, reduce fossil loads, make hydrogen, whatever else you want to do.
We've been talking mostly about jet fuel, and I think there's for good reason, because that's where the market has really taken off first. But you mentioned like this whole category of utilization in chemicals and fuels. It's broader than just jet fuel. You can use your CO2, and if you want other big markets, right, you can use CO2 to make ethylene. You can use CO2, combine it with hydrogen, and make synthetic natural gas. So outside of E-Jet, on your what's dumb, what's not dumb rubric, how do you think of the other possibilities?
By the way, I would encourage people to take a look at a report that we wrote a couple of years ago on CO2 recycling at the Center on Global Energy Policy, in which we looked at the thermal pathways and the electrical pathways, and we ranked them as a function of like stuff that's expensive and stuff that's really expensive and stuff that's in the money today. So people can go take a look at that. And again, like we started with, cement and concrete's in the money today. Among the things you can make CO2 into, ethanol is basically in the money today. Carbon monoxide is basically in the money today. And there is a real carbon monoxide market in the world. So there's things that you can do today that make sense. In addition to jet fuel, which is being driven by this sort of policy and operational need, something similar is methanol, e-methanol. And the reason why is because methanol is going to be an important maritime fuel. About 2.5% of global emissions are shipping stuff around the world with boats. And it turns out that they need a clean fuel too. As we've talked about before, some of that will be hydrogen, some of that will be LNG and renewable natural gas, some of that will be ammonia, but a lot of it will be methanol. And turning CO2 into methanol is something we are going to do. And in fact, we're starting to see that. There's companies like CNX, for example, that is a spinoff from Maersk. Maersk has created its fuel company again. They had a fuel company back in the past. They've got a new one now. And they're starting with biomethanol, which is, again, the smart place to start, but they are planning very much to go to e-methanol. When the technology is better, when the production lines are large, when the costs are reasonable, then that's something you can pick up. And like any other of these discussions, you start focusing pretty quickly on geographies. Where does it make sense to do this? Does it make sense to do this in Mombasa and Kenya, where they've got a lot of wind, solar, and geothermal? Does it make sense to do this in Chile? Does it make sense to do this in the Gulf Coast, where there's lots of available CO2 and there's cheap natural gas? Where do you start thinking these things through? So it's not this ubiquitous, like everything is made everywhere all the time, super cheap and easy. You end up making new production lines and new production hubs, and unsurprisingly, companies are starting to scramble. Countries are starting to scramble. They want to get the market share for the production. They want to get the market share for the manufacturing. They want to get the market share to monetize their renewable resources. And all these things are happening right now.
Okay, so methanol, I agree. And methanol, it shares a characteristic with e-jet, right? Like you've got a big transportation market. Transportation is a big portion of global emissions. There's pressure on that industry to decarbonize. And so there's probably room for a green premium in the early days to buy down the cost ultimately to be something competitive. So it looks like aviation. I'd say the one thing that to me is different about maritime versus aviation, I'm curious if this is your perspective as well. Aviation has moved faster a little bit here, in part because it's a little closer to a consumer product for the most part. And at the end of the day, that seems to be where the most pull is for green premiums on these types of products. And so you can have like some of what you see happening in aviation world is that airlines will be the buyers of the E-jet or whatever it is, could be biosaf. And they'll pass at least some of that cost on to a large customer of theirs, like, I don't know, a McKinsey or something like that, who flies a lot, wants to reduce their, emissions and is willing to pay a bit of a premium. So you kind of can see how that premium flows through the value chain. It's a little bit, it's one step removed typically if you're in maritime, if you're doing cargo shipping or whatever. And so it seems like it's coming along there, and Maersk has been a big part of that because they're pushing methanol pretty hard. But one step behind in part because of just being a step further from the consumer.
I think everything you've said is true. I would add, though, that it is also one step behind because the regulations hit harder for aviation quicker. 2027 is a pretty near-term deadline. The International Maritime Organization is going through a very similar kind of thing, but that looks more like 2035, 2040. It's going to happen, but there's a little more time to tie your shoes and figure out what makes sense. There's three other quick chemicals that I would go after in addition to what we've been talking about so far, jet and methanol. One of them is urea, which is a massive fertilizer market today. That is super cheap and easy to do. And in fact, there's a couple of big plants around the world that do that today. In Saudi Arabia, for example, SABIC, the chemical company there, has been taking CO2 and recycling it. They're recycling fossil CO2, but they're still recycling CO2. And that works. And that has reduced the footprint of that facility. That market will saturate pretty quickly, but it's a near-term place to act and a good one. A second thing that people are coming after is one you mentioned, ethylene. Here, the reason is not because it's cheap and easy. Quite the opposite. Turning CO2 into ethylene is wicked hard.
And ethylene itself is cheap. Like that's the other problem. It's a huge volume commodity chemical, very cheap.
Right. But the reason why people are doing that is because the technology is straightforward, actually. And a company like Dow, they might not want to do this automatically, but they surely know how to do this. So for them, the question is not what, the question is when. They're like, when we have customers who will pay the green premium for green ethylene, we will take CO2 and recycle it and make green ethylene. And they are already doing things like carbon capture and green hydrogen and electrification, like they're already chasing these things. So for them, they're like, well, we can do this other thing too. We'll do it when it makes sense for us.
And just to be clear for people who are not familiar with ethylene is a major input into plastic. So lots of plastics sort of are born out of ethylene. As always happens in the chemical industry, it's like a series of things that go downstream of that. But the way you can imagine that green premium playing out, at least in my mind, sort of similarly, you got to find the sort of consumer brand downstream of that in plastic world, who's using a lot of plastic, who wants to decarbonize their supply chain.
Right. And companies like LanzaTech are chasing that market. They have hacked the genomes of bugs, and those bugs turn CO2 into stuff. And one of the things they're trying to turn it into is ethylene. But they're also chasing like isobutanol or something like that. Like there's this whole raft of chemicals that you can turn CO2 into. It's not an electrical pathway, but it's a really smart pathway. They're using the natural world re-engineered to do this job. On the far other end of the spectrum, there's basically the guys who are like, we can throw it into a big Fischer-Tropsch unit. We're going to make synthetic syngas. We're going to make syngas out of CO and hydrogen. We're going to make the CO out of CO2. And then we're just going to run it through the chemical processes we understand to make whatever it is we want. And we're going to see some of that happening too. Part of the reason that turns into market is because you have existing infrastructure you can use. So if you're the German government, you're like, what are we going to do with these jobs? What are we going to do with these assets? What are we going to do with our chemical manufacturing? We could offshore all that stuff to a cheaper place, Or we could recycle CO2 and keep the jobs and keep the revenues and keep the IP. So these enter into the discussions as well. So like everything else in climate, it ends up boiling down to really who pays. Is it taxpayers? Is it ratepayers? Is it shareholders? How much of everybody pays what fraction of stuff? And in the same thing, like when do you do it? Where do you do it? It's not do you do it. The math tells us we have to do it, but when, how, with whom, where, those end up being the interesting challenges.
All right, so we've covered two categories here of utilization, fuels and building materials, or like built environment materials from concrete to building materials. Are there any others that you think are worthy of inclusion here? Because people are talking about using CO2 to, as you said, you could make almost anything with it theoretically.
So there's two other categories I want to give to your listeners. One of them is the not crazy stuff that is a little bit over the horizon, okay? So one example of that is polycarbonate, which is a potential substitute for glass. So there's a bunch of things that we make out of glass today. You can make that out of CO2, even though there's no CO2 in glass. You have a material swap. So you use less of one kind of material that is energy or carbon intensive, you use more of another one that's built out of recycled CO2. Polycarbonate glass is an example of that. Turning it into carbon fiber and making synthetic rebar is another one. You displace structural steel, some fraction of it, by putting these other materials in, okay? For those pathways, it's a short length. Those are, again, small margin commodities. It's hard to make a lot of money or business doing that, but you have an existing market. If you can get the offtakes, if you can get people to buy the green premium, you can do what I just said. So that is not turning CO2 into stuff that already has carbon. That's turning CO2 into stuff that's a replacement for something else. And that is part of sort of a broader sort of material substitution strategy that many countries, companies, and governments are trying to figure out, how much of that should we do? That is challenging, but again, straightforward. It's not necessarily cheap or easy, but it's straightforward. You know how to do every aspect of that. The final thing is kind of the over-the-horizon stuff, the mad, far-field science, the, we're going to live in some Marvel Cinematic Universe future where everything's made out of carbon composites. And, Wakanda and Iron Man are both making recycled CO2. That's kind of the world. That is not crazy. It's just farther away and harder. So, for example, we know how to make CO2 into graphene. Graphene is a super structured, super light, super durable, super electrically conductive material. It's like a version of buckyballs, basically. We know we can do that. We can do it right now at gram aliquots in laboratories. It's hard to spin that into a fiber that can be used by a fighter pilot. We're not in that world yet. But there's good reasons to want to do that. If you can actually turn CO2 into those materials, they're hard to make, but boy, are they valuable. They're $100,000 a ton if you can make that stuff. So there's this high margin materials, high margin business, small volumes today. The interesting question is, if you could make graphene for cheap and at volume, what else could we substitute? Could we stop using metals in cars? Could we make bridges out of this stuff? Can we make space elevators? What else can we make out of this stuff? And that creates an fictional, optional future that's very enticing and potentially really fun.
Right. You can make it into carbon versions of carbon fiber that are superconductive, and you could imagine, not literally superconductors, but very conductive. And so you could imagine replacing copper on wires and all sorts of things. Both technically difficult and economically difficult today.
Right. So there's a slightly academic topic that's sort of kicking around the electric gauntlet universe that you described around reconductoring. Can you take existing rights away, get rid of the old copper wires in there and put in something else, right? And there's something else. There's a question around that. What's the trade-offs in terms of cost and performance and all that stuff? But these sort of, superconducting carbon structures are a thing you could do. If not now, maybe in 15 years, maybe in 20 years. And the list goes on. Can you start building buildings out of carbon composite instead of concrete? These are, I think real questions. So when we imagine a universe in which we're recycling 100 million tons of carbon dioxide a year, yes, some of that will probably still be going to jet planes, but some of that might be going into industries that do not exist today, that go into products that do not exist today. And part of the reason to spend the money on the innovation ecosystem, on the infrastructure, on the labor force, is to make that possible. We'll see if it materializes or not, but I'm not going to bet against it. You don't bet against tech. The tech gets better. So the question becomes, what do you invest in? When do you invest in it? What's the smart play? I look forward to joining you in 5 or 10 years to discuss that.
It's literally my day job is trying to answer that question. The last thing I want to talk about just briefly is the infrastructure side of this. We talked about at the beginning how there are 5,000 miles of existing CO2 pipelines. On the other side of it, though, there have been a couple of pipelines that have been already proposed and in development in the Midwest, Summit and Navigator, mostly to take ethanol-based CO2 to sequestration sites. And they've both faced a fair amount of opposition, local opposition, and all the challenges that we face in any time we try to develop horizontal infrastructure in the United States. It's not dissimilar from what happens when we try to build transmission lines, for example. So to what extent does that pose, you think, a real challenge for this CO2, whether utilization or sequestration future, our ability to build the infrastructure required, the midstream required to get it from where we capture it to where we use or sequester it?
This is a very real concern. There are ways to work through it. I believe we will overcome some of these challenges and problems. There will be places where we don't. And we're sort of running that experiment in real time. So let me talk about a couple of examples where I think we are seeing what this could look like. One of them is there was an announcement just a couple of days ago, a portion of the Summit pipeline, a company called Tallgrass, that's going to capture CO2 in Nebraska and store it in Colorado. They are repurposing an existing natural gas pipeline to do that. There has been a back and forth about a community benefits package and an agreement. A group called Bold Alliance or Bold Nebraska has been sort of intervening into this process. There's been questions about how do you represent the landholders in a fair and just way, all these questions. Punchline, they cut a deal a couple of days ago, and they made a community benefits agreement that agrees to like a transparent monitoring process that gives money to NGOs and groups in the community that would benefit, that trains first responders on how to do this, plus, once the thing's operating, a royalty agreement so that the landholders get some value. I expect we're going to be seeing more of these kinds of things. That's not yes in every community, but it does mean that there will be some communities that opt in because they get the benefits themselves. So watch this space. This is no panacea or done deal, but that becomes a template for saying yes, and we don't have a lot of templates for saying yes. A second thing that you can do is exactly what happened basically with the Keystone Pipeline. Keystone Pipeline was fought, for better or for worse. It died, it was killed, and that was replaced with people moving oil by train. Like the stuff didn't stop moving around, it just became more expensive to ship it and a different kind of risk profile. We're seeing that happening right now in Europe, where basically instead of doing pipelines, they're doing barges. They're putting CO2 on boats and shipping it down the Rhine. And the reason why is because they can't get a pipeline through Germany. Like Germany's our people will never say yes to this, so we're just going to put it on boats and store it in the North Sea. That costs more money, but low friction in the population. There's a way to get to yes. The last thing that I think is going to happen is as people start to see what this actually looks like, they go, oh, that's what you meant. I didn't understand what you were talking about. And so now that I understand that the risks are low, the costs are low, we can get some additional jobs in our community, that there are good actors and they can be regulated well. Once that starts playing out, there's an opportunity for more yes. I am not in any way, shape, or form cavalier about this. I don't want you to get the wrong idea. This is not an inevitable glide path to the future. This is something you have already seen, Shale, in other dimensions. We're having a hard time permitting transmission lines, solar projects, wind projects, onshore and offshore. As we start putting these things into the field, in theory, there's no difference between theory and practice, but in practice there is. And we're learning that we have to get all of society to work together to make these things happen. I'm not cavalier about it, but I'm also pretty optimistic it can be worked because we're going to see this reproduced over and over and over again. If we want a just, verdant world, we're going to have to do this work. And it's as true for CO2 infrastructure as it is for all the rest of what we got to do.
All right, Julio, we're out of time, but I look forward to having this conversation again with you in 5 years from my graphene home, which has been made with direct air captured CO2.
Yes, well, I will be in my space bubble, orbiting the Earth, also made out of graphene and powered by CO2 synthetic fuels, and we can share a synthetic cocktail then.
Sounds good. Thanks, Julio. Julio Friedman is the chief scientist and carbon wrangler at Carbon Direct. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Learn more at preludeventures.com. This episode was produced by Daniel Waldorf. Mixing by Roy Campanella and Sean Marquand. Theme song by Sean Marquand. I'm Shail Khan, and this is Catalyst.